This is network calculus analysis of microbursts in data centers. So it's just an initial, some initial insights there. This is work done with Paridika Kayal and Nachanan Longsambum. Nachanan wanted to be in the session, but it's 2:30. No, it's now 3 o'clock. I don't know if that happens. So this is research supported by Huawei Canada. So the problem is that of microbursts. So microbursts are short-lived traffic spikes that cause packet loss and high delays in data center networks, even at low link utilizations. On the right-hand side, you see kind of traffic from an output port of a data center over a couple of minutes, and here you see the bursts. These are kind of these big spikes that appear. These we would refer to as microbursts. So the problem of microbursts has been studied in the last couple of years, 5-6 years. Many insights have been gained, but there is a lack of a comprehensive understanding, meaning people really don't know where it's coming from. Yeah, and so that's what we're trying to do in this effort. Trying to study the root causes of microbursts and actually, using network calculus models because they capture these transient effects very well, and then provide some guidance. Yeah, I don't know if that's the goal, to provide guidance on prevention and mitigation. So there are many possible causes of microbursts. Here's a list, so I will not touch on actually here I only touch on one of them. Fan-in, shift of bottleneck, scheduling, higher layer protocols, then mechanisms in large segment offset, offload in smart NICs, application traffic, flow and congestion control. So many of these efforts exist. So what I'm doing here is just introduce some terminology, and then I try to introduce a metric for traffic burstiness, so to say, talk about what makes a microburst. Then I get into application traffic, and then have actually an example of microbursts using a fan-in example using actual traffic. So here's the context that we're in. That's all familiar. So let's just network calculus. We have arriving traffic. This shows the traffic rate over time going through a network element. What is this here? A network element with rate C, and then generates then output traffic like this. Now in the network calculus, we use these cumulative functions, A of t for arrivals, D of t for service, and then the service is described by what we know as a service curve. Yeah, and then given an arrival function and the service curve, the departures can be expressed as an interaction between arrivals and the network element described by the service curve, and this interaction is the min plus convolution. So that's one concept. The next one is what I'm using here. It's kind of very simple model for an output for a switch port. It's a buffered link that is a queue here with a fixed queue that operates at a fixed rate C, is work conserving. By default, uses a FIFO. Has no buffer overflows, and offers an exact service curve. Yeah, and the previous example that I had was also the equality for exact service curves. So then we get as the arrival function. This is not easy to use. The arrival function.
Using position would be pointing to the screen.
The arrival functions and the service curves, then I can compute the departure functions. The difference between the two is the backlog. Yeah, so that's all familiar that's familiar to all of you. So the question now is how to detect microbursts, and I'm using here very old traces. This is from an IMC paper from 2010, using kind of 1 million packets in each trace. So I'll give you an example. This is what we saw earlier. So very clearly here in this sample here, we see this shows the traffic rate over short time intervals over a period of time. We see here that these are the spikes, clearly microbursts. Also here, we see 2 bursts there, different trace. Also here, yeah? And here, clearly no microbursts. It's very bursty traffic, but it's this gigantic burst. We would not see microbursts. But how about this one? Is this a microburst? Or this one here? Yeah, it's just a lot of kind of you have this spike here. So I argued that kind of if you want to make an analysis of this in some methodic way, we need a metric, yeah, for the presence and severity of microbursts, and the metrics what should evaluate the burstiness at different time scales and ideally be scale free. And so I'm considering three, or we are considering three metrics. The first one is, I call it burstiness curve. Yeah, so I mean, these are not new concepts. Burstiness curve, that is for an arrival, for traffic trace with an arrival function A, gives the most traffic that arrives in any time interval. So this is here the burstiness curve for an interval of length tau. It is just the worst traffic kind of that happens in a time interval of length tau. And as you know, this here can be just simply the deconvolution of the arrival function with itself. Yeah, so that's then from there I can get a peak to mean ratio function. Yeah, so that's kind of the peak to mean ratio that was used a long time as a constant, but here I express it as a function of the time interval length. So it becomes a function of the interval length tau, which is then the ratio of the burstiness curve divided by the average traffic in interval of length tau. Then lastly, the maximum backlog function. So that's a kind of an imaginary maximum backlog that would occur if we had a link that operated at rate r. Yeah, so the maximum rate r here is the maximum backlog with rate r is just the supremum here of the difference between arrival and departures, which since we have an exact service curve, this is not to the screen. This is the screen. Yeah, that. Yeah, so it's there. I point there. It's the departure is then the. I give up. It's the convolution, and the service curve again is just this rate function. Yeah. So I want to say more about the. Oops, this doesn't go. Can I go backwards? I want to say more on the burstiness curve and the maximum backlog function. So the burstiness curve, as I said, at interval length t gives me the most traffic that arrives in any time interval of length t. Yeah, so it provides a measure of burstiness at different time scales. Yeah, so and it is the smallest sub-additive envelope, or if you like, arrival curve. Yeah, the smallest sub-additive arrival curve that you can generate for a traffic trace. And this concept is from a paper with Knightley, Reg, and Zhang from 1995, where we called it empirical envelope. And we did it because the term burstiness curve was taken. I just took the liberty, because this is very descriptive, to call it burstiness curve. It expresses this quite well. Another comment here on the maximum backlog function. So here's a little lemma, and let me know if you this is not new. For an arrival function A and an exact service curve S, the maximum backlog can be exactly expressed as the min plus deconvolution of the burstiness curve with the service curve evaluated at 0. Yeah, so and with that now, so this is what gets why this is interesting, is within a service curve with rate r, the maximum backlog then, kind of this deconvolution, becomes this term here. And this is here the negative Legendre transform of the burstiness curve at r. And the Legendre transform is interesting because in min plus systems theory, it plays the role that is analogous in some way or similar to the Fourier transform in classical systems theory. And it performs it's a transform that moves a function from a time domain to a rate domain. Yeah. The maximum backlog function is also related to the work. This is Stephen Lowe's PhD work, or published in 1991, where he defines the maximum backlog as this supremum of this interval, where m of t is the instantaneous arrival rate. Yeah, so there is a certain, since this is an integral, this is pretty much kind of cumulative, and this is the reason why we didn't call the empirical envelope back then burstiness curve. The term was taken. They used this term. Yeah, but I believe that has kind of, it's after 30 years, I think flipping that term is better because there's no burstiness here. Yeah, but it's a great metric. So I'll give you an example for these for the traffic. So this is a traffic trace here. I now look at time intervals between 0 and 100. Here we have the three metrics. Yeah, so we have the burstiness curve here. The red line here is the average traffic, and you see that the kind of the burstiness curve gives you much more than this. The peak to mean ratio, yeah, for intervals of longer than 10 seconds. So the burstiness goes away. You get a ratio of 1, but it's kind of quite high in this lower regime. And this is what the maximum backlog function gives you. This, of course, so I plot here the maximum backlog function. This is not as a function of R. This is as the function of arrival rate of R, the rate of the link, divided by the average rate of the traffic. With that, it becomes scale-free on the x-axis, and that is then 1 divided by the link utilization. Yeah, it looks like, but I want to be increasing R in this direction, so it's 1 divided by the link utilization, which means here at kind of 10 means 10% link utilization, you still have a significant backlog here. Yeah, and even for 20, that's 5% link utilization. There's backlog here. And this one here is, this would be 95. This one here is 50% utilization. Yeah. So so these are long intervals. Yeah. So 100 seconds. This is a 1 gigabit per second network here. So that's too long for kind of considering bursts. If you're looking at a smaller time interval. Yeah. So now switch from 100 seconds to a time frame of 5 milliseconds. Yeah. So then you really see how the burstiness arises in this traffic on short time scales. See, this is the average traffic in 5 milliseconds. This is the worst case that happens in 5 seconds. And if you're looking at the peak to mean ratio, you see here that in this interval up till 5 milliseconds here, the burstiness, the peak to mean ratio is 50 to 1. And that's significant if you recall kind of video, compressed video has something at most 20 to 1, yeah, 10 to 1, 20 to 1. So this, and even for very short time scales, much larger. The backlog function does not depend. It looks at the entire frame. So it doesn't, the picture did not change, but I want to draw your attention to this linear decrease of the maximum backlog. Yeah. As kind of plotted in this way, because I use that as an indicator of the presence and of a severity of microbursts. Now, for other kind of, now I apply these maximum backlog functions for different traces. So here we see microbursts. Look at this linear decrease here. Look at this one, this kind of a medium burst here. You see the backlog completely disappears below kind of someone here, kind of this is probably 8% or so utilization. This one does not have microburst, and what you see is at lower utilization there is no rate. So kind of getting a picture like this, because it's scale-free, indicates the microburst and the size of the microburst you can see on the y-axis. So that's what we're working with. So now we're trying to study the burstiness of distributed machine learning traffic. And the starting point is you were working with traffic traces. It's very difficult to get public traffic traces for data center traffic. So this one here is kind of one rare exception of data that is available. It's from a paper from the buffer sizing workshop at Palo Alto from 2019. We call them, the authors are from the University of Cambridge, so we call them the Cambridge traces. They are traces for 4 types of applications in this setup. So there are 6 systems and 1 switch. They're all 10 gigabit per second links. So we have 1 server and 5 client machines here. They're all the same machines. And the traffic is measured at this point. Yeah, have in mind that if you're looking at burstiness, we're looking at this traffic. The burstiness is happening over here, but we are tabbing here, so at the output. Yeah, so I have that in mind when I look at the data here. So this is the total amount of data. This is the traffic rate over some time intervals for the entire trace. And this is the macroscopic view. 150 seconds of the trace has 6 million packets in it. You don't see, that's what people usually, they do statistics on this. Yeah, and then it's what we do is looking at a small time scale. Yeah, looking at only 30 milliseconds of traffic, and then the traffic looks like this. Yeah, so this is the traffic rate, and yeah. So in color coded here, I hope you can see it in red, we have the traffic from the server to the clients, and in blue, the traffic from the clients to the server. And you see that the traffic appears in sequences of bursts. There's some regularity to this. Yeah, did you see it? Yeah, you can really see. And so this is what we're going to continue to look at, these small timescales. And if you look over here, it looks the same way. Yeah, so it's essentially always 10. 10 is the maximum rate. So it's essentially bursts of traffic being sent back and forth. And these are now the metrics for the traffic from the server to the client and client from the server. So it's kind of a separate the directions. Looks pretty much identical, yeah, because in the end, you can already saw it before, it looks kind of, the amount of data sent is quite similar. Here's the peak to main ratio. It's not that bad, actually. It's not that high. Yeah, it's at most, it's not even 3 in the worst case. Yeah, so it's not that bursty traffic, and that of course is reflected in the maximum backlog function. You see it flattens completely out. Yeah, so at a utilization below 50%, no backlog. Yeah, so this is actually not bursty traffic. Yeah, so even though it's quite interesting. So next thing is now, yeah, let me maybe go back, is next thing is now using this to scale the network up. Yeah, we want to not look at, the measurements are for 5 clients. If we scale up to 100 or so, we don't only go up to 50, what is happening? Yeah, so for that, we need a model. That's kind of, we need a model to feed a simulation system. And to get this, we kind of further dig deeper into the traffic trace, and we split it up into different clients. Yeah, we have the PCAP files. Yeah, the PCAP files are available. We can use the IP addresses to look at the traffic generated by each client. And then we see these things. So the top line is the aggregate traffic. That's what I showed you earlier. And it's only for the same 30 millisecond interval. But now this traffic over here, the first row, is the aggregate, the aggregate of what's happening in the by the clients. And you can see that they're all active for some period, and then they get at some time later this traffic coming back. Yeah. Using this, we can generate a model and really understand what the application. We actually looked also at the application code, which is also published. It's the TensorFlow. It's a TensorFlow 1.15. So it's an older TensorFlow version. Kind of a very simple machine learning application. Yeah, it's a very simple application. I have details if you are interested. The application works like this. So the server does some processing. Then it sends data to the workers. These are the parameters of the model. And it does so, that's quite interesting, in batches of 2. So it only sends data to 2 workers. Once it's done to send the parameters, then it moves to workers 3 and 4. So I switched now terminology from client to worker, because that's the machine learning language. So it does it in batches, and that is important later on for the behavior, what we'll observe. Then the workers do their computation. Yeah, they come up with results, which are the gradients, and they send them back. And that's the moment then when you would observe a micro burst, yeah, with some overflow. That's when the traffic is aggregated. So we can now, this is how it works, and then it repeats. Yeah, and that's what we observed in the traffic. So we can distinguish different phases. There's the server processing. There is the submission, the transmission of the parameters to the workers, which happens, as I said, in batches. This is all more or less deterministic. Yeah, it happens in batches, but we can compute it. The worker processing time was somewhat random, and we modeled it by uniform random results. Then the transmission of results we simulated. Yeah, so we didn't model this. And then the server then waits until everything has been transmitted and then starts again. So that's our model. It's a model to feed a simulation. It's not an analytical model, but it actually fits. It's kind of a very good match for the actual traffic. This is the actual traffic for kind of, I use here the same 30 millisecond intervals. They all look the same. And so we get this burstiness curve, the peak to mean ratio, the maximum backlog. Down here this is obtained from the simulation using the model. Yeah. kind of, you cannot tell the difference. Yeah, so it's kind of a very good model. So we can use this now, this one here, this to scale up and see what happens if we have more. Yeah, and so this is where we're getting into how much time do I have? Because 2 minutes. Okay, then I have to cut something out. The multiplexing. So now fan in refers to the multiplexing of concurrent flows that belong to the same application. And so what people generally say is that this is how it's generally defined, but I want to emphasize that it's not only the concurrency of the flow, kind of of the transmissions, it's also that the bursts of their transmissions have to be aligned. Otherwise, you don't get this fan-in effect. And actually, the example of this traffic here, this TensorFlow traffic, is a counterexample. Yeah. And then the piece that I skipped now is there is kind of a network calculus argument that you can make to test for alignments. And that essentially consists of comparing, if you're having a group of flows, if you're comparing the burstiness curve of the aggregate to the sum of the burstiness curves of the constituting flows. Yeah, and depending on their relationship, you can actually make a statement whether traffic is aligned in a worst case fashion or not. So to make it then come to the end, for our example, kind of for this traffic that we have, we get that here for a 30 milliseconds interval, the kind of the blue line here is the burstiness curve generated. This is only the traffic from the workers to the server. Yeah, that's the one that creates potentially the buffer overflow. This is here the traffic from the actual burstiness curve of the aggregate, and here is the worst case pattern. And if we blow this up here, this to 5 milliseconds, you see that only in a very short time interval, this here would be kind of the worst case alignment. And in fact, this one here is the line, the rate of 10 gigabit per second. That's what the rate is captured. This here would be all flows sending simultaneously would be 50 gigabit per second. Yeah. So what do we see? Yeah, in this application, yeah, we now scale this TensorFlow application from 5 workers up to 50. What we see is the maximum backlog never changes. Yeah, it keeps the same. Yeah, and so why does this happen? And it happens the way that this application works, kind of when the parameter server sends these parameters to the workers kind of in batches, it serializes when the workers start their work and send their results back. So that results in a sublinear increase of the utilization. So here for the number of workers, the right-hand side, the black curve is, the left-hand side, and the black curve is the link utilization. You see the link utilization goes up and saturates somewhere at 80%. What this really means, as the number of workers are added, the contribution of a worker here, the rate at which the workers send traffic decreases from 1 gigabit above 1 gigabit per second to below 200 megabits per second. Yeah, it's kind of a counterexample of a microburst. This traffic, this application will never generate microbursts. Yeah. So to conclude, we have additional work, and I would like to talk about it, but I would need the whole day. Just the morning. So there's still more work to do. So we're now looking at this was a very simple machine learning application. We're now looking at more complex data. We get the data from our industrial partner. So we get pretty much a small testbed network, but 100 gigabit per second links, and kind of this ring all reduced, linear all reduced data. And the models are more complex. Yeah, so we have the amount of parameters and convolution layers is much larger. Thank you.
Very quick question. So do you know whether TensorFlow needs this information from the workers in a serialized manner, or is it already optimized to not produce microbursts?
No, they don't know about. Oh yeah, I repeat the question. So the question is whether this Okay, what
Whether TensorFlow is optimized to not do microbursts?
yes.
Or whether
Is TensorFlow optimized to not do microbursts? The answer is no, because there's no awareness of that. But so this is now the thing where things get interesting. So there is this ring all reduce, kind of it's a different exchange of parameters and linear. So it's particular. So what could create microbursts here is it's the presence of this parameter server, which is still used in practice. So I'm told, but there are other methods that don't have a parameter server. So this mechanism I don't know why TensorFlow, this earlier version of TensorFlow had this distributed TensorFlow had this grouping, which performs this. So what happens now is kind of we're looking the reverse. We're looking at the traffic generated by the particular machine learning type of machine learning application and configuration, and then go back and then see the traffic and then make recommendation backwards. I think, yeah, I don't know. That's actually the answer to that. But there is kind of this gap between traffic and the machine learning program. Yeah, so that's kind of, there's a gap of understanding, and we're trying to get into that. And this is with the conjecture that there is that the you have to look at the actual applications. Yeah, and the dominant application in commercial data center is training of deep learning models.
I think that was a very good.
Okay, thank you. Appreciate that. Very kind.
Just a quick question. On your slide 25, that's the comparison to the burst case. And I'm wondering whether it may be possible to also include comparison with a good case in which, right, very close.
What is a good, what do you mean as a good? 25. Yeah, so I didn't really discuss this slide in detail. So this is here, we're kind of, so yeah, so this is kind of the worst case. If the worst case is much it's very, if the worst case and the stacks of the per flow envelopes is similar to the aggregate, the actual burstiness curve of what you observe, and it's possible if the traffic is not bursty, they will be identical because it's smooth traffic. Yeah, so but if the traffic is bursty, then they experience the burstiness. So I don't understand what you mean by good.
Right, so there is the actual mix of the traffic. You have the worst case if they superimpose the worst way. You could have a good case if they superimpose that reference case.
Yes, yes, good. That's a very good. Yeah, so the question is, so here I look at the worst case traffic, the other one is looking at the other direction, what would be the most benign version of this traffic. That is interesting, but the project, I'm so supposed to study overflows. So that's not.
Tell you what's possible in the best case.
Yes, so you know the question of independence is actually very. Oh yeah, but I'll continue that with you later. Sorry.
There is a question on the bridge.
On slide 22, so Yang Chengting asks which kind of model is used on page 22 to generate the sun trace.
22. It's the wrong slide. Oh, they're looking at the, yeah, you see, I deleted a slide, so maybe they're, this is probably, is this the one they're meaning to?
So I'll just ask him.
Yeah, that's the, I deleted a slide, that's, and I still went over time, yeah.
Yes, this one.
What was the question?
The question was which kind of model is used to generate this trace?
It's you see, again, it's not an analytical model. It is essentially this model here shown on the previous slide. That is the model that we use, where we use a deterministic latency for the server processing, then this deterministic delayed but staged because of the grouping by the parameter servers over here, and here's a uniform random variable. in the range of parameters that we observed in the data, in the entire trace. This one here, the green part, the sending of results, happens. This is simulated. It comes out of a simulator. Yeah. So we essentially generate a source model for a simulator, not one that it can be used for an analytical model, which would be, by the way, a very interesting thing to do. Does that answer the question? I hope it does. Let's not ask it. I hope it does. Yes, thanks. Thank you. Thank you. Oops, yes.
Like at home. So much.